And it's my distinct pleasure to start the day with our second keynote for the conference. And we are grateful to have Marcus Aguilera from NVIDIA. He's recently moved to NVIDIA. So this is like, I believe, his second day or first week, I think, at the new job. So Marcus is a researcher and a distinguished engineer at NVIDIA, and his research interests span all aspects of distributed systems. He has done a lot of seminal work in the area of storage systems as well, and also distributed systems in fundamentally both from theory perspective as well as from the practice. So he's one of the few researchers who is well known in the community for bringing both systems and theory together. And so it's always interesting to read his papers that are built on both foundational theory as well as building a proper real systems. He has been working in a wide range of industrial research labs, starting from Compaq, and then he moved on to HP Labs and then MSR Silicon Valley. And then he also co-founded the VMware Research Group and then Broadcom. And recently he joined NVIDIA as a distinguished engineer. Marcus is also one of the few researchers who has been very visible both in academia as well, in addition to his technical background in industrial research labs. So he has been a program chair for all top conferences in the systems area, including OSDI, FAST, SOC, and also DISC and OPODIS, right? He will be serving as a program chair for NSDI, which is another top conference in our area, and it shows that he has a really both background in both academia as well as academic research, as well as leading industrial research products and research in general, right? So he received his MS and PhD both from Cornell University, and today he will be talking a bit about disaggregated memory systems and the revival of memory research. So Marcus, thanks again for joining us, and now the floor is yours. We are looking forward for your keynote.
Great. Thank you very much, Pramod, for the introduction. And let me just start by saying that I'm very grateful to be here. Everything that I say is my own view. It does not reflect the views of NVIDIA. It's just the standard disclaimer here. And so minimize this. I'm going to start with a simple observation that new technologies tend to refresh research areas, and there are several examples of this on this slide. I'm not going to go through every one of these examples, but I wanted to highlight one of them, which is networking research, core networking research. So in the mid to late 2000s, networking research was very jaded, pretty much because the internet was working well already, and it was very difficult to deploy new ideas because the internet is a combination of different administrative domains, and everyone has to agree to adopt something new. And so it was very hard to do innovative, interesting core networking research at the time. And all of this changed when the hyperscalers, like companies like Google, at the time Yahoo, Microsoft, and others, decided to redesign their data centers, including their data center networks. And they came up with new hardware, new problems, and new constraints that completely revamped and revitalized research in core networking. And today we're seeing a new technology coming that will do, in my opinion, the same for memory research. And when I say memory research, that includes both memory hardware and computer architecture, but my focus on this talk will be the parts of memory research that touch on shared memory algorithms and systems and operating systems. And that technology is disaggregated memory. And so I'm going to spend some time explaining what I mean by disaggregated memory and also the technology that is behind it. And I wanted to separate also the concept of disaggregated memory with the specific technology that is coming up, because most of the research is about the concept, and the technology, of course, is important to drive and make the concept real, but other technologies will come in the future as well. And provide a model for disaggregated memory that we can use to think about it in a more abstract fashion, and the differences that we see between disaggregated memory and regular memory and the applications. And finally, with the time that I have left, I'm going to talk about the systems that we built, and I'm probably going to run out of time there, but I'm just going to go into a few of the things that we've been doing in this space as well. And so that's the overview of the presentation today. And so let me start with the simplest thing, like what is disaggregated memory, right? And disaggregated memory is memory that sits outside the physical confines of the enclosure of a server. So we can see on the left here a host node. I'm going to use the words host node or server interchangeably here, but these are the machines that are sitting in a data center. And of course, these machines have processors and local memory. And we can see on the right that there is a chunk of memory which is sitting outside of the box, outside the host and the node, which is connected to the host and node via an adapter. And that memory is separate from the local memory that sits within the host. And so there is still some amount of local memory, and disaggregated memory is apart from that. And once you have memory sitting outside, of course, you can connect it to multiple different hosts and nodes. And this allows the same memory locations to be shared between these two things, these two hosts, or more. And in fact, in this figure, I'm showing an idealized version of the previous slide, but I added also a switch. So the switch allows connecting more than a larger number of hosts to disaggregated memory. And in fact, with the switch, we can connect a larger number of hosts to a larger number of disaggregated memory modules. And these modules are no physical boxes that are sitting elsewhere, and they may fail independently because they are connected to separate power supplies. But the issue of failures of disaggregated memory is a very interesting one that I'm going to go back to later in the presentation. And I should notice that there is a fabric that exists connecting the hosts, which is shown here in orange, that is separate from the fabric that connects the host to the disaggregated memory. And in the future, maybe one day these things will converge, but just the nature of what you need to connect disaggregated memory to the host make it so that these fabrics are still separate from each other. So for example, the network fabric is currently in data centers Ethernet, right? Whereas the memory switch fabric is dedicated for just memory, and there are startups that are working on different versions of this fabric. And the fact that there is two different fabrics connecting the hosts makes it also very interesting, and the way that communication happens over these two fabrics is different. And so I'm going to get into that as well later in the presentation. So what is disaggregated memory useful for, right? And well, the simplest application is that it provides additional memory capacity for the host. So in addition to the local memory that you typically buy for your hosts, you have this thing sitting outside that gives more memory. And that additional memory is kind of interesting because it can be used for extending the memory in an online fashion. And by that I mean you can add more memory to a machine without having to power down the machine. And that's usually called like hot add memory. And that would be extremely difficult to do with the local memory of a machine, right? Because you'd have to kind of open the chassis and put memory on the DIMM slots while the machine is functional. And so this is very hard to do, but with disaggregated memory, that becomes viable. And that's what I mean by online memory expansion. It also allows the notion of memory pooling and memory sharing that I want to illustrate in the next slide. The idea of memory pooling on the left here is that we have the disaggregated memory, which is shown in green here, and it gets assigned to hosts on a need basis. So if nobody needs the memory, no host needs the memory, the disaggregated memory is just sitting there idle, but it's available to anyone who needs it. And this is, I like to think of this as being analogous to having like books in a library that you can borrow when you need it. So instead of buying the books for everyone, instead of having memory which is just private to each host, you can have the books sitting in the library and whoever needs them just borrows them. And what that means is that you can improve memory utilization and thereby reduce the cost by using disaggregated memory. More specifically, what you can do in your system is that you can provision the local memory for each host on the average need. And whenever the host goes over the average need of the local memory that it has, it gets the rest from disaggregated memory. And if you do the calculation, as long as the host don't need memory at exactly the same time, if there is no correlation about when you need memory, then the fact that you have this book sitting in the library or the memory sitting in disaggregated memory allows you to buy less memory in your system and still be able to serve all the needs from all the hosts. And I wanted to distinguish memory pooling from the notion of memory sharing. So with memory pooling, there is really no sharing of memory in the sense that the disaggregated memory areas are mapped to different hosts without any overlap, right? And so this is the dashed line here. Like the top part is being mapped to host number 2, and the bottom part is being mapped to host number 3, but there's no single location that is mapped to both hosts. With memory sharing, which is shown on the right here, you can have actually the same pages and the same cache lines being accessed by multiple hosts at the same time. And different from pooling, what this allows you to do is provide a communication mechanism for this host, which is via shared memory. And while memory pooling is useful for improving memory utilization and lowering the cost, memory sharing is useful to lower the communication costs. And I'm going to go into that in more detail a little bit later. Before that, let me just give you a brief history of disaggregated memory. And it started in the 90s, where there was an observation that the network was faster than disks. And so if you would want to create a system where you can swap or page your memory to the network, it would perform better than paging to a local disk. And these were systems that I'm calling paging-based systems that are basically using this externally sitting memory as a swap device, right? And that is good in many ways because those solutions are completely transparent. Like you don't need to redesign your application because the operating system takes care of doing the swapping for you. However, of course, swapping tends to be fairly inefficient because every time you need to access some data which is not locally present, you have to take a page fault, you have to copy the data in, and then you have to continue executing. And in the process of doing so, you have all sorts of things happening, like the execution pipeline gets flushed and the caches get polluted and so forth. Not to mention that taking a page fault consumes a large number of cycles in your CPU, and so your execution essentially gets a hiccup every time you take a page fault. So, but those are paging-based systems in the 90s. In the late 90s, we see the proliferation of a technology called RDMA, or Remote Direct Memory Access, which is a technology that already existed with InfiniBand, but later that technology was commoditized to be able to run on commodity Ethernet in the mid 2010s. Now, these are systems that, contrary to paging-based systems, they require the application to do I/O to access the data. And so, in other words, if you have a host that wants to access the memory which is sitting outside, the host has to issue an RDMA I/O operation to read the data. And when he wants to write, it has to issue an RDMA I/O operation to write the data. And so it's not transparent to the application because the application has to program using RDMA. Of course, you can also implement a paging-based system using RDMA, and I would classify this as being a paging-based system. In 2009, this was the first paper that proposed the notion of a byte addressable system where the processor can directly issue loads and stores on memory sitting outside, right? So this was not true in the 90s with the paging-based systems because there, every time you access the outside memory, you cause a page fault. It was not true for our DMA-based systems because you have to issue, processor needs to issue an I/O. In 2009, in HP Labs, they proposed the idea that a host should be able to do a load and store directly on memory sitting outside the box. There was no notion of sharing memory at the time. It was mostly used for extending the memory of a host. 2013, Intel comes up with a rack scale architecture that did not succeed, but it was the first attempt to realize disaggregated memory, which is byte addressable. And finally, in the 2020s, we see Computer Express links versions 2 and 3 being proposed. So I think I covered this already, talking about the paging-based systems. And so, but just to reiterate, it's based on swapping or virtual memory. And it's very slow, but it's transparent, which is a reasonable trade-off. And I talked about the I/O-based systems as well, which is not transparent, but it's much faster. So, and I should mention that with RDMA, we can think of two different types of disaggregated memory. So here, the figure on the left, we have a memory blade which houses the disaggregated memory, and the hosts are accessing memory in the memory blade via RDMA. And I like to call this physical disaggregation because the memory blade is essentially dedicated to provide memory. It does not run application code on it. The figure on the right, which I'm calling local disaggregation, essentially allows this green area, which is the area of disaggregated memory, to be actually part of the memory of individual hosts, which when combined provides the totality of the disaggregated memory. And so you can see that physically it's not disaggregated, but logically the machines will have the ability to access that memory, which is kind of sitting outside the box, but it happens to be in another machine which can run application code. And the difference between physical and logical disaggregation has implications to failures and fault tolerance, which I would say would not make these two abstractions completely equivalent, but from the point of view of programming, it's very similar. Like the RDMA that you use, IOs that you use in both cases are similar. Of course, some of the things that you need to do to set up RDMA, like connections and so forth, are also different in these two cases. But by and large, like the mechanics of the RDMA is the same. And yeah, what's interesting about disaggregated memory, like I mentioned before, are the systems that allow the processor to do loads and stores directly on the memory. And that's a thing which is kind of coming up very recently, and that made disaggregated memory systems extremely interesting from my perspective. And so I covered what's in the slide already. So let's move on. Let me zoom in a little bit more on the Computer Express Link or CXL technology. And this is an industry standard which is being driven by a consortium that has the same name. And they produce specifications of this standard for 3 versions already. Version 1 in 2019, version 2 in 2020, and version 3 in 2022. And I should mention that CXL is not just about memory disaggregation. It allows to do other things. Basically, what you can do with the CXL is that the CPU can directly access memory sitting on PCIe devices and vice versa. So notice that traditionally CPU can only access memory which is sitting on DIMM slots that are right next to the CPU socket. These are kind of through a dedicated connections. Actually, the DIMMs connect directly to the pins of the CPU. And so the CPUs can do loads and stores directly there. CXL allows the CPU to access memory on the PCIe device. So the PCIe device is a bus which is intended for I/O. It's not intended for memory. And CXL allows that memory to be accessed in a cache coherent fashion. And there are several different types of CXL devices. And so type 1 refers to a device that access memory attached to the CPU, which is the opposite direction that I just mentioned. You can think, for example, of a GPU, you can think about a NIC, for example, that access memory which is sitting on the DIMM slots. With type 1 devices, you can think about a CPU accessing memory that is attached to the device, for example, with a GPU. Though a GPU can also access the memory which is sitting on the CPU if it's a type 1 device as well. And type 3 devices are like type 2, but the device is dumb in the sense that device is not allowed to address its own memory. So think of just like a memory expander. Because with a GPU, which is a type 2 device, the GPU is actually using the memory that is local to it. Whereas with a type 3 device, you could just have a memory expander and there's no access happening on that memory other than the access by the CPU. And the current products that are in the pipeline for CXL are focusing on, at the moment, type 3 devices, but more products and use cases are coming up as we speak. So one use of CXL is as a local memory expansion, and this has nothing to do with disaggregated memory. So, but it's the thing which is picking up at the moment. And this is motivated by the fact that the memory which are sitting on the DIMM slots is extremely limited, right? Because there is a small number of DIMM slots per memory channel, and there's a small number of channels, and the capacity per DIMM is also limited, and the cost is non-linear. As you get to higher and higher density DIMMs, the cost per gigabyte increases. So for example, if you go to 64 to 128 gigabyte DIMMs, you're doubling the memory capacity, but the cost is multiplying by something like 4, right? And so that is kind of unfortunate, which means that if you want to build a machine that only has memory sitting on the DIMM slots for a large quantity of memory, it's going to be super expensive. And in fact, if you look at the bill of materials for a server sitting in a data center today, like a majority of the cost of that server is its memory. Like it's not the CPU, it's not the NIC, right? It's the memory. Memories become very expensive, and at the same time that there's a need to provision more and more memory to servers because servers need to address larger and larger quantities of data. I like to say that big data is moving to memory, and so that requires big memory, and big memory is very expensive. And so what CXL allows you to do is to add memory beyond the DIMMs. Now the memory is going to be slower because the DIMMs are sitting right next to the CPU. As I mentioned, there are dedicated CPU pins connecting the CPU to the memory, whereas on CXL, the memory is sitting on the PCIe bus. And so it's going to be slower by 100 to 200 nanoseconds. So typically access to local memory is in the order of 100 nanoseconds, but with CXL, it could be 200 to 300 nanoseconds for a local memory expansion device. This could be very compelling for CPUs with high core counts. Like AMD is producing CPUs with 192 cores, and there's typically a desire to provision a certain amount of memory per core, something like 16 gigabytes or 32 gigabytes per core, going to 64 gigabytes per core. But if you have such a large number of cores, then you're going to have large quantities of memory in your system, and you can't put this all on DIMM slots. And as you increase more and more core counts, there's the need for more and more memory sitting on the same node, on the same host. So that's the CXL memory expansion, and that was available in the specification of CXL version 1. But with versions 2 and 3, you get the support for memory pooling that I talked about previously, and version 3 support for memory sharing across hosts. And in all of these specs, the memory in CXL is cache coherent. So I'm going to have something to say about cache coherence in a later slide, but the specs do provide mechanisms to provide cache coherence. So these are the mechanisms that I described for disaggregated memory as I went to the history. And so we have paging or swapping, which is transparent but slow and no support for shared memory. We can have RDMA I/O operations, which is not transparent because the application needs to issue RDMA operations. The speed is faster, but it does allow for shared data. And in fact, RDMA has supports for things like atomic operations like fetch and add and compare and swap that helps designing shared algorithms over that memory. And finally, with CXL 2 and 3, you get transparency, you get fast speed, and you also get sharing in CXL version 3. That's why disaggregated memory has become a much more interesting topic as of recently. So how do you think about disaggregated memory? No, beyond the technology, CXL is a specific technology, right? But we need to think about disaggregated memory when you design algorithms or systems in a more abstract fashion. And the way I like to think about it is we have a system that has a bunch of different processes that are running as part of an application or distributed application. These processes are being shown here as P1, P2, and P3. And they have some amount of local memory that is only accessible to them. This is private memory to the process. But they also have access to disaggregated memory, which all of these processes or a subset of these processes may have access to. And in addition to that, they have a communication fabric where they can send messages to each other via message passing. And this is like Ethernet, right? Now, in the same host, there can be multiple processes running, and those processes can be sharing the local memory amongst themselves, but not sharing the local memory across hosts. So this is being shown as P1 and Q1. They're processes in the same machine sharing the local memory. But the disaggregated memory is being shared by everyone. And disaggregated memory may have access control that allows only for security, that allows only a subset of the processes to access different regions. So this is shown here on the right. For example, on the first green block at the top, only P1 and P2 is allowed to access that, and the last one, only Q3 is allowed to access that, and so forth. And this can be achieved through a combination of mechanisms in the local operating system of the processes, as well as the hardware that provides the disaggregated memory. Okay, so now that I described and I give an introduction to disaggregated memory and I gave a model for it, I want to talk more deeply about what are the differences between disaggregated memory and regular memory and the implication for these differences. Before I continue, I guess I can stop and see if there is any questions. I think this would be a good time to ask those questions. I cannot see the chat window from my laptop because I am sharing the desktop here. So if there are any questions on the chat, please, it would be great.
So
People cannot.
we don't have any questions as such. I believe I'm checking Slack as well. So for the
Okay.
time, I don't think we have any questions. But if there are any, please feel free to write it to the channel or leave it at the chat as well. So
Okay. Sounds good. Let me see if there's a way for me to access the chat, but I think it's going to block part of my screen.
I mean, I can always relay the questions to you but as of now, I don't see any questions.
Okay. Sounds good. I I can see the chat window here, but I have to explicitly open it, and so I'll do this at a specific points in the presentation. I do not have access to the Slack at the moment. Okay, so let's continue then. Let me just close this. Okay. So the first difference I wanted to highlight when you have disaggregated memory is that a process or thread of an application has two fundamentally different ways to share data with each other. They can use the disaggregated memory to do the sharing, or they can use message passing, right? So we have one process running host 1, another process running host 2. The way you typically design a distributed application without disaggregated memory is that these two processes are going to be passing messages to each other, like sending messages over TCP or UDP or broadcasting messages. When you have disaggregated memory, you have an additional mechanism that allows the two different processes in two different hosts to communicate, which is to just share data in disaggregated memory. And this is interesting. Oh, before I go to the slide, let me just mention. This is interesting because when it comes to when it comes to distributed algorithms, um, essentially the literature and everything that we know about distributed algorithms is there's a dichotomy there. So there are distributed algorithms for shared memory, and there are distributed algorithms for message passing. And those things are taught independently of each other, and they're used independently of each other. For example, algorithms for agreement or consensus, right? Paxos, for example, or view stamp replication, it's a message passing algorithm. But there's also algorithms for consensus in shared memory. And those have a fairly different flavor, right? In shared memory, the processes tend to agree using atomic operations like compare and swap, for example, or using things like splitters. And those are all like algorithmic constructions to get to these algorithms. If you look into a textbook of distributed algorithms, like Nancy Lynch has a textbook that she uses to teach distributed algorithms at MIT, the book is divided into two parts. There's a part about message passing algorithms, there's a part about shared memory algorithms, right? And so the way that at least the theoreticians think about these two different mechanisms is very separate. But once you have disaggregated memory in your system, you can design applications and even algorithms where processes can communicate and share data in these two different ways by passing messages and by sharing memory at the same time. And so, and that of course brings a fundamental question like, do we get more power when process can do both of these things than if the process can only share memory or only pass messages? And there is a theoretical result in distributed computing that says that these two models are equivalent, or shared memory is equivalent to message passing. And so if they're equivalent, like what's the point of combining them? Like you combine two things that are equivalent, you still get the same thing, right? Now, if you look at exactly what this result is saying, and this is the paper by Atia, Barnoy, and Dolev, where they show this equivalent, what they're showing is that if you have an algorithm for message passing, you can simulate this algorithm in shared memory, and vice versa. If you have an algorithm for shared memory, you can simulate this algorithm in message passing, and thereby get the algorithm for the other model. So, however, this equivalence is only computational. Like, yes, the algorithm is going to work, but it's not going to be the fastest algorithm. So it's not equivalent in terms of performance. This equivalence also requires a majority of correct processes in one direction. So for you to be able to simulate a shared memory algorithm using a message passing system, you need to have a majority of correct processes in the message passing system. And that means that algorithms that tolerate more than a majority in shared memory, for example, could not be simulated using message passing. Right? Also, this equivalence doesn't hold if the sharing can be restricted by access control lists, like I mentioned before. So yeah, the fundamental question still stands, like, what is the additional power that we get by combining these two different models? And people have studied this recently. And before I get into the details of the results, let me mention that when disaggregated memory is being shared, there are two conceptually different ways to specify how things are restricted, how the sharing is restricted, using a shared memory graph, which is shown at the top, or using access control lists. So using a shared memory graph, we create a graph where the vertices are processes, and there's an edge between two different processes if intuitively there's a connection between them. And the connection allows the processes to be sharing memory. So, for example, let's take a look at process Q here, right? So the vertex labeled Q has edges to R and edges to P. That means that Q can share memory with R and P. And by implication, like R and P can share memory with each other as well. So think of this as being memory which is sitting adjacent to Q that both Q, R, and P can access. And so once you have a graph like this, you can specify the subset of processes that can share memory with each other by looking at the edges, at the vertices and the vertices that are directly connected to it. For example, SQ is a set that consists of Q and the two processes P and R. So in other words, P, Q, and R, and they all can share memory with each other. So that's the shared memory graph. Another way to specify a sharing restriction is using access control lists. So basically, we're saying that no region 1, R1 in disaggregated memory can be shared by process P and Q. Region 3 can be accessed by process Q, R, S, and T. So the shared memory graph is more applicable to what I called before logical memory disaggregation. And remember, logical memory disaggregation, you have one host actually exposing parts of its memory to the other host, where the first host can be running application code, right? And so, and that's why it makes sense to talk about these connections. So again, like Q is connected to R and P, there is memory which is belonging to Q, which is exposed both R and P, and so they all can share memory that way. Whereas access control list is more relevant for physical memory disaggregation. And so now, given these two ways to specify sharing restrictions, we can ask questions about, how about solving consensus? Like, we know that solving consensus in a message passing system requires a majority of correct processes. So here F is the maximum number of processes that can fail, and N is the total number of processes. And you can show, and people have done this in the distributed computing community, that solving asynchronous consensus using even randomized algorithms requires a majority of correct processes. In other words, F has to be less than N over 2. Now, that's using a message passing system. If you're sharing memory, you can tolerate the number of failures up to pretty much everyone except one process. Like F can go, the number of processes that can fail can be up to everybody except one. Okay, so with shared memory, you can solve consensus with a large number of failures beyond a majority. How about if you have both of them, like both message passing, shared memory? Of course, that's trivial. Like if you have both, you can just use the shared memory, forget about message passing, and if you get F equals N minus 1, right? The interesting part is when the sharing is restricted. For example, if it's restricted by the GSM graph, then we can solve consensus with up to F less than this formula here. Now, if you look at this formula here, you'll notice over here that the denominator of this fraction here is going to be bigger than 2, right? Which means that this entire fraction here is going to be less than half, right? And if you take 1 minus something which is less than half, you have something which is greater than half, right? So we can have, and this parameter h here is a property of which is called the vertex expansion of GSM. So we can solve asynchronous consensus in a system with both message passing and shared memory. In other words, in a system with disaggregated memory, with more than a majority of correct processes, even though you have restrictions on the sharing. And of course, if that restriction was none, then you could go up to F equals N minus 1, right? But this is kind of a general result based on the vertex expansion of the graph. Another interesting results, and these results are coming from distributed computing community, is if you want to implement a register, it's called a so-called single writer multi-reader register, which is shared by everyone with sharing restrictions, but you want to implement a register that does not have sharing restrictions, you can do it in certain cases. And let me mention that once you implement a single writer multi-reader register, this is a register that can be written by one process and read by multiple processes. Once you implement such a register without sharing restrictions, then you can pretty much solve consensus and implement other synchronization algorithms because there are known shared memory algorithms that use such registers. And there have been papers by Hatzilakos, Hu, Tweg, Atiyah, Kumari, and Schiller that shows when you can implement such registers that are shared by all when you have sharing restrictions on the underlying memory. And in the first set of results, the maximum number of failures that can be tolerated depends on a property of the graph, whereas with the more recent paper, you can do this provided up to the maximum F such that F failures do not partition the processes for a majority. So I would refer you to these papers if you want to go into more details, but basically it's showing a conditions that are needed and sufficient for you in the case in the last paper for you to be able to implement a register without sharing restrictions when you do have sharing restrictions. Okay, so this was the first fundamental difference between having disaggregated memory is that processes can communicate both by sharing memory and by passing messages. I want to highlight that another fundamental difference when you get disaggregated memory, which is the fact that disaggregated memory is slower but bigger than local memory. And this leads to the notion of memory tiers. It's lower than local memory because it's farther away, it's going over the PCIe bus, at least with CXL technology. It tends to be bigger because once you're putting the memory outside the box, you can put a whole lot more memory than you can put on a memory connected to a server, to the CPU server. So once we have that type of memory, which is slower but bigger, at the same time we have local memory, which is faster but smaller, we can think of the system as essentially having two tiers of memory, right? There's a fast tier, which is the local memory, and there's a slow tier, which is aggregated memory. And when you're running an application over the system with two different tiers, it's desirable for the hot data, which is the data which is being frequently accessed by the application, to be sitting on the fast tier. Now, this, by the way, assumes no sharing, like there's no need for share the data. This is just about using disaggregated memory as an additional memory capacity for one host. And if you have those two different tiers of memory, you want to put the hot data in the fast tier and the cold data in the slow tier, right? So because that will give you the maximum performance. And you also would like to do this in a way that doesn't require applications to be changed. Like you don't want to write a version of malloc that tells you, I want now to allocate memory on the fast tier versus on the slow tier. Or you could do that, but it just would require a huge burden to the applications to decide what's hot and what's cold. And these things, in fact, even if you can make such a decision, can change over time. So what's hot now can be cold in the future and so forth. So ideally, you'd like to find a transparent scheme that will place hot data on the fast tier and cold data on the slow tier that doesn't require changes to the application. And what I'm going to talk about next generalizes to more than just two tiers. You can imagine having like 3, 4 tiers, but two tiers allows you to understand the foundations. And I also should mention that the notion of tiering is not exclusive to disaggregated memory. For example, if you have persistent memory, not PMEM, you also have two different tiers of memory because PMEM is lower than a local memory. Or if you have CXL memory expansion, which is not disaggregated, you also have two different tiers of memory.
Marcos, may I interrupt you, I guess, for just for timing purposes? Maybe it's possible to wrap up in, let's say, 5 to 10 minutes or so that we leave at least 5 to 10 minutes for questions?
Yes,
Okay.
sure.
Okay.
Yeah, we do. And so I was talking about it's nice to have these transparent solutions, and you can achieve transparency using virtual memory. And essentially, the OS can remap pages to the slow and the fast memory based on whether they are hot or cold. And this can be done without having to change the applications. However, there are several interesting questions when it comes to doing this, which is how do you track access to pages? Like you want to know if pages are accessed frequently or not to know if they're hot or cold. And there can be mechanisms based on page poisoning, which essentially means you unmap the page and you create a page fault for some subset of the pages so that you can collect stats about who is accessing the page and when. You can use access bits on the page table, or you can use hardware performance counters. But there's also the metric that you use for the temperature. So it could be the number of accesses or the recency of accesses. And what is the criteria to classify as hot and cold? What is the threshold? Like if you have the number of accesses greater than X, but what should X be? Or the recency being more recent than Y, what should Y be? And there are also questions about how to move pages without perturbing applications. And so I would like to mention there's a number of existing systems that have looked into these different problems and proposed an actual, holistic solution based on different choices of this trade-off space. And this being illustrated here, but I don't want to go into the details of this table, but I just want to mention that it's a very interesting and active area of study as we speak. One thing I wanted to mention, and I'm not going to go very deeply into this, but it's the notion of weaker cache coherence. And of course, modern processors have many cores with caches, and disaggregated memory data in disaggregated memory is going to get cached at the core. And CXL technology provides for cache coherence of disaggregated memory. And cache coherence has a textbook definition, which I'm going to leave on this slide for your reference. I'm not going to go into the details of cache coherence definition here. But what I do want to mention is that CXL3 supports cache coherence of memory being shared across hosts. And it leverages the existing coherence mechanism that each processor already has, but it adds two new mechanisms, which is called back-invalidate and snoop filters. And the details of this is super interesting, but I'm not going to cover it exactly here. I'm going to leave this slide as a reference for you folks to look at, but this shows what happens if host 2 wants to access a location which is being cached by host 1. It wants to write to something which is being cached by host 1. And this is all the different actions that happen by doing this. So essentially, there is a snoop filter, which is essentially a directory sitting in disaggregated memory that tells who is caching what. And you have to go consult the snoop filter, and you have to do invalidations of existing caches, and CXL will take care of all of that for you. So though I'm not going to the details of this, let me just mention that coherence is going to be very hard to scale to a large number of hosts just because coherence traffic gets excessive after a while. And so I believe that CXL disaggregated memory will not be fully cache coherent, even though the specification allows it to be cache coherent. But in practice, making cache coherence across all the hosts will be very low performing. Not to mention that the snoop filters themselves take a lot of memory as well. Which brings the question of, if it's not going to be fully cache coherence, what is the level of coherence that we're going to get? And one possibility is no coherence at all, which I think is interesting in its own right, but there are partial levels of coherence as well. So the notion of federated coherence provides coherence only within each host, not across hosts. But there's also the notion of having some regions of memory that are coherent, but the rest is not. You can have a small region of memory which is coherent and the rest is not coherent. And now you need to develop applications or algorithms that make use of these weak coherence models. And I think that's super interesting to explore. The last thing I wanted to mention, and I know I only have a few minutes left, but I wanted to mention the last fundamental difference between disaggregated memory in local memory is the fact that disaggregated memory may fail while your processor is still running. So if you get your local memory fail while the process is still running, it tends to be a catastrophic event, though no, the memory itself will try to fix using error correcting codes and so forth, but end to end, if the memory fails, essentially the application is hosed. But local memory failing is really difficult to handle. Disaggregated memory is sitting a little bit further away from local memory, so it makes sense to design a system where if disaggregated memory fails, not all the hosts connect to it will fail. And this has been studied in some early theoretical papers where the failures of disaggregated memory can be masked through replication. But that requires a huge amount of memory to do this, because even if you have two replicas, you're essentially doubling the amount of memory that you require in your system, and that's too expensive. What we need to do here, in this case where memory can fail, is to design data structures that are gracefully degrading. So the assumption is that disaggregated memory is going to have chunks of areas that fail separately because they may be in different chassis, for example, and you may have a fraction of your disaggregated memory failing. For example, 1/3 of your disaggregated memory has failed, but the other 2/3 are still available. And we want to design data structures that can tolerate that. For example, if you have a tree data structure, you might want to put and replicate just the root or the top level. So whenever you have a failure in disaggregated memory, you don't have the completely loss of your tree or your data structure in general. And I think that's a super interesting area to study. We have built some interesting systems, and I'm not going to cover this because of time constraints. I'm just going to briefly mention some of the things that we've done without going into the details. So we have been looking into improving the performance of data processing frameworks using disaggregated memory by using the sharing ability of disaggregated memory. So that's one. In particular, take a system like array, and we basically show how to make array faster using disaggregated memory. Another interesting thing I wanted to mention, also given the amount of time that we have, is that we are able to build better logs or better pub subsystems using disaggregated memory. And essentially, we're using disaggregated memory to keep the shared logs. And you can think of this, how this is working is you have several message brokers. They're all appending messages to the shared log in disaggregated memory. But I'm going to just leave the slides for your consultation here afterwards. And I'm going to conclude to leave space for questions. So let me mention for the conclusion that full-fledged disaggregated memory is coming, and what I mean by that is that processors can directly access disaggregated memory using loads and stores, and this is enabled by a standard in a consortium called Computer Express Link, and that is refreshing and be refreshing the research being done in memory systems due to the several fundamentally different aspects of disaggregated memory, which is the ability to have a shared memory with message passing communication mechanism, the ability to have memory tiering, the need to address weaker coherence models when you have disaggregated memory, and the need to handle failures of disaggregated memory. And this is going to lead to new systems and applications. I have briefly mentioned distributed data processing frameworks as benefiting from disaggregated memory and distributed share logs. And there are people working on other things like databases that are benefiting from disaggregated memory and other things, right? And I think there's going to be more and more applications going forward. With that, I'm going to stop and see if there's any questions people wanted to ask.
Thank you. It was fascinating talk. So I would leave the floor open for questions now. So if you have questions, please feel free to ask them either by sending it on chat or also you can use Slack. Okay, so we already have a few questions in place. I would start with the first question from Benson Mute. There's a lot of legacy software, much not yet ported to use RDMA. Are there any good practical examples that take advantage of CXL 3.0 capabilities? Not sure if you have measurements. So he's mostly interested in figuring out what kind of practical examples where we can actually take advantage of this CXL 3.0 capabilities.
Yeah, so CXL 3.0 is not widely available. So looking for examples of these things, no, concretely speaking, they're not there. I think what is available these days are more researchy works on using CXL 3.0 to share data between hosts. But talking about legacy, what you can imagine doing is taking an application that has multiple threads and placing those threads across different hosts. And that allows you to scale the application to a number of threads which is much higher than being able to run in a single node. That, of course, assumes cache coherence of all the hosts that are running this application. And it does support and does assume that there's some kind of operating system that allows you to do this. Such operating system doesn't exist yet that allows you to start an application and fork off and span new threads that are executing on the other node. But conceptually speaking, that is something which is possible to do. So if you're asking about how to run legacy applications with this technology, that is the thing which I would consider doing. It does require some research on the operating system part, but if you do it right, it shouldn't require you to change the applications. Of course, there's going to be some performance implications to doing something like that that needs also to be studied carefully.
I guess maybe the author or the sorry, so maybe I can take up more questions, but maybe I just wanted to make a comment over here as well. I guess maybe he's referring here would be is the performance aspects because they are asking about the measurements. So in particular, I think the problem with the 3.0 technology is that even though it allows you to do this byte traceable read and write, but the coherence traffic too, if you really want to do track everything, right? As you said, like there's a protocols, coherence protocols for snooping or directory based, they would also will not scale quite well because you need to do something selective tracking of the shared memory locations, right? So maybe that's was another aspect that he might want you to comment on it, I guess. Yeah.
Yeah, for sure. Like I did mention about the scalability of cache coherence. I would not imagine doing this across 20 different hosts, but doing across two hosts, for example, would be viable. And of course, you would not be doing this across hundreds of threads on two different hosts. Maybe um, you can buy a host or a processor that has a smaller number of cores, and you can add to the multi-threading capability by having a second host instead of buying a more expensive CPU to do this. But I would not be using the CPUs that has the highest core counts and having such a large number of threads because the coherence traffic is going to explode. The raw performance numbers as well, by the way, latency going to disaggregated memory is higher than local memory, and there are several different prototypes going out there, but I think it's premature to comment on the performance that we're seeing today because performance would tend to get better in the future. But what we're seeing is like 4, 5, 6 times lower than local memory, right? In the future, that might be like 2 or 3 times lower. I don't expect to be less than that. And so there is definitely going to be performance penalty. And by and large, if your application is using your caches correctly and well, then that latency to the memory can be mostly masked. But that is a big assumption that the caches are able to function effectively there, right? But now, one cache performance is already 100 times faster than memory cache, right? And so, if that memory becomes 2 or 3 times lower, a one cache performance still becomes super relevant here. And if your application can be designed to exploit local cache as well, that should be hiding the larger latency of memory. And so, but easier said than done. But that's at least conceptually speaking what could happen, right?
Thanks. I think yeah, so he said thanks. Maybe then move on to the next question. It's from Amit Kolander. So thank you for the good talk actually. And his question is more about the memory capacity bottlenecks in today's OS and CPUs and what kind of research directions or work you think would be interesting to work on future in this area actually. Yeah. So mostly about the future directions in terms of OS and CPU architecture to overcome this memory capacity bottlenecks. Yeah.
Yeah, I think the tiering is super important to do this, right? Because in order to get the additional memory capacity, you're going to have slower memory, and then you have to do a very good job at memory tiering. And there are existing mechanisms in the processors, like having the access bits or having performance counters, can be extended better to provide better ways of tracking to find out about cold and hot pages. And there's work going on as we speak about doing this co-design of hardware and software for being able to do better tiering. But I think that's a super interesting area. And it needs to be done because the additional capacity that you get with CXL is going to be slower.
Sounds good. I think this ties nicely with the next question because this is quite good actually. So the person actually is Song Jiang. So he's asking, yeah, exactly. With memory tiering, you will have applications who have experienced more uncertainty on their execution performance because sometimes they will access from slow memory location or the fast memory location. So which would which would, in their opinion, discourage people from applying these technologies to scenarios where actual performance prediction is required. So when you are talking about strict SLAs, I think they are referring to that. So what would you comment on those applications where performance prediction is actually crucial? So do you think
Yeah,
tiering?
no, two things. No, first of all, the working set needs to be fitting into local memory. Like if you have your working set being the entirety of memory, then it's going to be a tough one to be able to have SLAs and SLOs being met. The second thing I wanted to mention, this problem already exists today with NUMA memory, because NUMA is much slower than local memory, and people are doing fine, right? So
Fine,
I
yeah,
think people do fine as well
they're
for
okay.
disaggregated memory.
Yeah. Okay, maybe I have a couple of questions also, which falls into my research area. So I'm actually interested in looking into the heterogeneous systems as well. So as you started with your assumption about disaggregated architecture, where you have a lot of hosts accessing this memory, so all hosts were homogeneous. So, and we know that our data centers are very heterogeneous in terms of computing, like from not only from the host processors like GPUs, sorry, x86 and ARM, but also we nowadays have GPUs, and they all have different coherence protocols, right? So if we try to stitch them together, what kind of challenges you think are there in terms of basically interoperating different memory consistency models is quite challenging. So how do you see adoption of CXL systems in heterogeneous data centers?
From the computer architecture point of view or the application
I think
systems point of view?
both, because actually the memory consistency models are then exposed at the language level also for the application programmer. So yes, also from the architecture point of view, because I think you talked about this fabric being connecting, and CXL, even though promises that we have same interface for all architectures, it's very difficult to actually combine these architectures, primarily because host level coherence protocols cannot be changed because they are highly optimized for their target architecture, but they need to talk to CXL over disaggregated memory, and the interface needs to respect the memory consistency model of CXL as well, which is a different like it also follows TSO kind of a semantics, but let's say if you combine this with weak architectures like ARM, for example, or GPU, for example, they have different architecture requirements as well. So to answer your question, I was thinking about more both from architecture as well as from the programmer point of view as well. Yeah.
Yeah, a couple of comments here, right? First, when it comes to the CXL mechanism for coherence, which is the Snoop filter and the backing validate. So that mechanism tries to leverage the coherence mechanisms that already exist inside the processor, right? And so when CXL sends a processor a backing validate message, the processor will have several cores and several different levels of caches, and the processor will use its own cache coherence internal mechanisms to handle that and ensure that the backing validate does the job correctly. And so, and in theory, if you have an ARM processor which supports CXL and an x86 that supports CXL, that should work just fine. In the end, what you're going to get is that you have a system with cache coherence. And however, when it comes to memory consistency, and this is second comment I wanted to make, is that memory consistency is orthogonal to cache coherence in many ways. Now, from the point of view of the application developer, of course, you have to take into consideration both things, both cache coherence and the memory consistency model. What you're going to get when you mix all these systems with different memory consistency models is the least common denominator. And you're going to have to program with that, right? Which typically would be something like weak coherence consistency with like ARM processor, for example. But you're not going to have to worry about cache coherence itself. And again, I want to separate two different aspects. Cache coherence is not going to be an issue. The issue is going to be the coherence model, the reordering of operations that may occur by the various different architectures. And Intel has its own thing as well, like TSO model versus not. And so you're going to have to worry about the least common denominator and design your application that way.
Okay, I agree with the second part of this, like the compound memory consistency that you are referring is the least common, but I disagree on the first one. But this is something we can discuss it offline because I need to convince you about the first one. But we can talk about this offline. I would wait for other questions to come in. Are there any other further questions from our attendees?
Ramon, we're slightly over time anyway.
Okay. Then I would suggest that then we thank Marcus now for his wonderful keynote.